students, myself Chaitanya, Assistant Professor, Department of Mathematics, Institute of Aeronautical Engineering. Today we are going to discuss an important topic from the course Probability and Statistics, and the topic of discussion is the fundamentals of probability. That is, we are going to be introduced with the concept of probability and the necessary properties and associated examples. So let us start the lesson without a delay. So before going to the definition of probability, we have to construct some prerequisites which are required to define probability mathematically. So we have to make some groundwork to define probability mathematically. So for that we need some prerequisites, namely random experiment, the sample space associated with the random experiment, and the event involved in a random experiment, and then mutually exclusive events, equally likely events, impossible event, certain event. These are the prerequisites which are required to define the probability, the phenomena of probability mathematically. Then we will define the classical definition of probability, and we'll see some examples and the problems related to that. So let us start the lecture without a delay. Random experiment. In our daily life, we'll come across two kinds of activities, namely random and non-random. Which kind of activities are known as random and which kind of activities are known as not random? Suppose if you take the event of the sun rises in the east, that is a well-known fact. The sun rises in the east and the sun sets in the west. These are completely predictable. We can predict them in advance every day with 100% assurance. These are called non-random experiments. So non-random means the experiments whose results can be predicted with 100% assurance are called non-random experiment. On the other side of coin, we'll come across certain kind of activities whose results cannot be predicted in advance with 100% assurance, but we can make some choices of possibilities. That means there are some experiments whose results cannot be predicted in advance, but we can expect what could be possible to happen. These kind of experiments are called random experiments. Examples are any competitive situation that you take is an example of random experiment. That means a sport, a game, or an exam, or any competitive situation is known as a random experiment. For example, if you take the experiments of tossing a coin, rolling a die, picking a card from a deck of cards, everything is a random because we have choices. If we toss a coin, the choices are head and tail, but we cannot say what happens exactly. In the same way, if you roll a die, there are choices 1, 2, 3, 4, 5, 6, but we cannot predict what happens exactly until the game is over. In the same way, you can take the cards game, playing cards game. It is also a random experiment. So any kind of sport or game or competitive situation or exam or business situation, anything you take, all are random experiments. Now, what do we mean by a sample space? Sample space is a set of all possible outcomes of a random experiment. That means if you are conducting a random experiment, you can list out all the possibilities associated with that random experiment. For example, if I am tossing two coins at a time, I could list out the possibilities: head head, head tail, tail head, and tail tail. So the list of all possibilities associated with the random experiment is called the sample space, and it is denoted by the letter capital S. So it is denoted by the uppercase S. Now, there are so many examples for sample spaces. The sample spaces associated with the tossing of two coins is nothing but head head, head tail, tail head, tail tail. Same way, you can list the sample spaces associated with the experiment, rolling a die, picking a card, etc., etc. Now, we are going to define what do we mean by an event. Let us consider R be a random experiment and S is the sample space associated with the random experiment. So let S be the sample space associated with the random experiment capital R. That means we are involved in a game or sport, namely capital R, and S is the list of all possibilities of the game capital R. Now we are going to define event of capital S. Any subset of the sample space capital S is called an event. That means any subset, whether it is empty or non-empty, any subset of capital S is called an event. So the power set of S gives us the set of all events associated with S. Every subset of S is known as an event. For example, if you take rolling a die, rolling a die means the sample space is 1, 2, 3, 4, 5, 6. Rolling a die means the sample space is 1, 2, 3, 4, 5, 6. And if we define an event capital A as getting an even number, the defined event is getting an even number. So the associated event is A is equal to 2, 4, 6 because on a die 1, 2, 3, 4, 5, 6 are the faces. Among them, the even numbers are 2, 4, 6 and hence the event is A is equal to 2, 4, 6. It is a subset of capital S. You have to understand capital A, 2, 4, 6 is a subset of the whole sample space capital S, that is 1, 2, 3, 4, 5, 6. And hence every event, that is the wish of every player, if you treat it as an event, the event is nothing but the subset of capital S. So mathematically, an event is nothing but the subset of capital S, and in general, an event is nothing but wish of the player who is playing the game. Same way, you can take another example. If you toss 2 coins at a time, if you consider the experiment of tossing 2 coins at a time, then the sample space is nothing but head head, head tail, tail head and tail tail. So it involves 4 possibilities total. That is head, HH, HT, TH and TT. Now some player is interested in getting 2 tails. So his interest of play is event getting 2 tails. If you list the favorabilities, that is A is equal to the set TT. So the set A is equal to 2 TT is the subset of the whole sample space capital S related to the game tossing 2 coins. So it is an event. So in the same way, you can define getting a single head, that is also an event, that is HTTH, and getting a double head, that is set HH, it is also an event. So in that way, you can define, you can observe the events as the subsets of capital S. Now, what do we mean by equally likely events? A set of events are said to be equally likely if there is no reason to predict one in preference to others. You know, in any game or in any competitive situations, you'll see sometimes the players, the opponents, or the players who are playing the game seems to be equally potential. Suppose if you take a cricket match between India versus Australia, it is always a 50-50 game. That means India is as equally potential as the team of Australia. In the same way, India versus England, both the teams are equally potential. Whether the bowling composition or batting composition, you take any criteria, both the teams are equally composed and hence both are equally likely. But if you take a cricket match between India versus Zimbabwe, you'll tell that India is more stronger than Zimbabwe. That means you are saying that India is more potential than Zimbabwe. So, if you take the example of India versus Australia, both teams are equal potential and hence both the teams are said to be equally likely. If you take the example of India versus Zimbabwe, India is more stronger than Zimbabwe and hence India and Zimbabwe are said to be not equally likely. So with this motivation, we can define 2 events capital A and capital B of random experiment capital R associated with the sample space capital S are said to be equally likely if their probabilities are equal. In simple, there is no reason to predict one in preference to other. That means you cannot say that A is stronger than B or B is stronger than A. So both are equal. So both have equal chances of winning. That means P of A is equal to P of B, then A and B are called equally likely. The example is head and tail of a coin. Okay, that you can take it because probability of happening head is equal to probability of happening tail. The same way you can see another example, getting an even number while a die is rolled has equal probability as the event getting an odd number when a die is rolled. So these two are also equally likely. Now we are going to see one more important definition, that is called exhaustive events. A set of events of capless are said to be exhaustive if their union is equals to the whole sample space. That means if you have a collection of subsets of capless, where S is the sample space related to the random experiment cap law. So the collection of the subsets of capless is said to be exhaustive collection if you write the union of all those subsets, the union should be equal to capless. That is, union of all the subsets in that collection should be equal to the whole sample space capless. Then the collection is said to be exhaustive. Now the next definition is mutually exclusive events. A set of events are said to be mutually exclusive if the happening of one prevents the happening of the other remaining events. That is, two events cap A and cap B of a sample space capless related to the random experiment cap law are said to be mutually exclusive if the happening of A prevents the happening of B as well as the happening of B prevents the happening of A. That means A happens, B will not happen, and if B happens, A cannot happen. That is, both cannot occur simultaneously. That is, A in section B will be empty. In mathematicals, we can say that A in section B is empty, that is A and B are disjoint. If you take the example of tossing a coin, if the coin turns into head, that means it cannot be a tail. In the same way, if the coin turns into a tail, it cannot be a head. So head and tail or a coin are mutually exclusive. In the same way, pass and fail are mutually exclusive events of an exam result. In the same way, win or loss are two mutually exclusive if you take the example of a tennis match. So mutual exclusive means preventing one another. If one happens, the other cannot. And if the second happens, the first one cannot happen simultaneously. This is called mutual exclusive. Now, we have prepared the ground to define the probability mathematically. Let us recap the things once. That is, first we started with the random experiment. Random experiment is nothing but an experiment whose result cannot be predicted in advance. That is, tossing a coin, rolling a die, and picking a card from a deck of cards. Next, sample space is a set of all possibilities related to the random experiment cap law. That is, if we toss two coins at a time, the possibilities are head, 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 tail, tail, head, tail, tail. Then we have defined equally likely events. That means whose probabilities are always equal. Mutually exclusive. If A happens, B cannot happen, and if B happens, A cannot happen. And in prior to that, we defined event. Event is nothing but any subset of S is called an event. Now, the interesting cases are the empty subset pi and the whole set capless. Empty set phi is also a subset of S as well as the whole set S is also a subset of itself. How could we imagine them? The empty set pi represents the impossible event, that means which never happens, and the whole set capless represents the sure event that the event always happens. So in that way we can understand the existence of capless and phi as events. Now we are ready to define what do we mean by probability. Let us suppose that there are n mutually exclusive equally likely elementary events of an experiment, a random experiment. That means the random experiment, if you take Kepler as a random experiment and capless is the sample space related to Kepler, Then let us suppose that the cardinality of S is small n, and every element of capitalist, the every event of capitalist, elementary event of capitalist are mutually exclusive as well as equally likely. That means if S contains E1, E2, E3, so on, En, all even E2, E3, so on, En are mutually exclusive. That is, no two events can occur simultaneously. In the same way, E1, E2, so on, En are equally likely. That is, P of E1 is equal to P of E2, that is equal to P of E3, that is equal to P of E4, so on, equal to P of En. All the n events have equal chances of occurring, equal probability. In that case, we can define the probability of an event capital A. That is, A is an event of capital S, a subset of capital S, and the chance of happening of A, that is the probability of capital A, is defined as n of A by n of S. That is the cardinality of A by the cardinality of S. That is the number of favorable cases of A by total number of cases in S. So this is the fundamental definition of probability, which gives us the mathematical uh, measure of probability. That means it is the first mathematical measure of probability. Being the probability is a general life phenomena, so this definition helps us to define it mathematically. Now, but the classical definition has its own disadvantages. Like if the sample space is infinite, then the denominator becomes infinity, and hence it becomes very tough to define the probabilities. So, in order to overcome those kinds, and also it assumes as the events are all equally likely, but in practice it need not be. It need not be. So, in order to overcome those drawbacks, it has been generalized, and another kind of definition for probability has been introduced by Mr. Kolmogorov of Russia, who is a famous statistician, which is known as Kolmogorov's axiomatic approach of probability. In this approach, unlike the classical definition, we define the probability as a function which satisfies three specific conditions. So, in this definition, we are going to see that the probability is a function and which satisfies three specific conditions. Let us see the definition. Let capital S be finite sample space, and a real valued function capital P from power set of S into real number line R is called a probability function. That means we have a random experiment of capital R and whose sample space capital S is finite, and we have a function P defined from power set of S into real line R. That is, the function P maps every subset of S to a real number. Now, this function is called a probability function if it satisfies the following three conditions. What are the conditions? The first condition, P of A is always greater than or equal to 0 for all A belongs to S. That means for every subset of S, for every subset A of S, P of A is always non-negative. So it is known as Axiom of Positivity. We can call it as Axiom of Positivity, which states that probability is always positive. That is, P maps every subset of S to a positive real number only. So this in simple, we can say that probability is always positive. And the second axiom states that as S is a subset of itself and P is the function defined from the power set of S into R, the image of S is always 1 under the function P. That is, P maps S to the number 1 on the real line. If we interpret it as, the meaning is the total probability of all events of the random experiment is equal to 1. That is, sum of all probabilities is always 1. And hence it is called as Axiom of Certainty. It states that P of S is equal to 1, that is, sum of all probabilities of the experiment is equals to 1, and hence the axiom is known as Axiom of Certainty. By this axiom, we can trivially observe that the probability of phi, the empty set, will be automatically 0. So it maps 5 to 0. And the third important axiom is the axiom of union. The axiom of union is defined to mutually exclusive events only. It states that if A and B are two mutually exclusive events of plus, then the probability of A union B will be equal to probability of A plus probability of B. That is, the probability of happening of A or happening of B is nothing but sum of individual probabilities. That is, sum of happening of A plus happening of B. P of A and B is equal to P of A plus P of B, provided that A and B are two mutually exclusive events of plus. That is, A and B are disjoint. If you draw the Venn diagram, A and B will be two disjoint events, and then P of A and B is equal to P of A plus P of B. So, from these axioms, we can easily observe that P of A complement and the plus P of A will be 1. That is, sum of A and its complement. The probability of A and its complement probability is always 1, because A and A complement are mutually exclusive and A and A complement are exhaustive events. Automatically, by axiom of union and axiom of certainty, it follows that P of A complement and P of A, the sum will be 1, and hence P of A complement is equal to 1 minus P of A. We can interpret it as the failure probability is nothing but 1 minus success probability. That means the probability of A being failed in a game is nothing but 1 minus the probability that A will succeed. So failure probability is equal to 1 minus success probability. The same way we can observe that if A1 and A2 are two events of plus such that A1 is subset to A2, then the inequality will be preserved. That is, the probability of A1 will be less than or equal to probability of A2. So if A1 is subset to A2, then P of A1 will be less than or equal to P of A2. So if you take an event A of the sample space plus of a random space log, then you will have automatically the event A complement, that is the favorable cases of A. If A represents the favorable cases of A complement represents the non-favorable cases of A. So, if you calculate the ratio of P of A is to P of A complement, then you will get the odds in favor of event A. If you calculate the ratio P of A complement is to P of A, then the ratio gives you the odds against A. So odds in favor of A is nothing but the ratio P of A over P of A complement, and the odds against of A is the ratio P of A complement over P of A. So now the question is, axiom of union is defined for two mutual exclusive events. That is, if A and B are mutually exclusive, then P of A and B is equal to P of A plus P of B. But what happens if A and B are non-mutually exclusive, and how to calculate their union probability? For that, the additive theorem on probability will answer. It states that if A and B are any two events, may be mutually exclusive or non-mutual exclusive, then P of A and B is equal to P of A plus P of B minus P of A intersection. That is, the joint probability of A and B is nothing but the probability of A plus the probability of B minus the common probability of A and B, the simultaneous occurrence of A and B. So, this law is called as additive law for two events. By analoging, we can understand the probability of happening of A or B or C, that is A and B and C, as P of A plus P of B plus P of C minus P of A intersection B minus P of A intersection C minus P of B intersection C plus P of A intersection B intersection C. That is, probability of happening either A or B or C is nothing but sum of individual probabilities, that is A, B, C, minus the double probabilities, that is minus A intersection B minus A intersection C minus B intersection C, and plus the triple probability, that is A intersection B intersection C. So in this way, additive law helps us to calculate the union probability of two events or three events. Now let us see some examples. First, in this problem, we are going to find the probability of a leap year which has 52 Sundays. So, the leap year can have the leap year will have 366 days. And if you divide it into weeks, that is, a week has 7 days, then we'll get 366 divided by 7, that means 52 weeks and 2 extra days. We'll be reminded with 2 extra days. Now those 2 extra days are 2 neighboring days. So the possibilities of those 2 neighboring days are Saturday, Sunday, Sunday, Monday, Monday, Tuesday, Tuesday, Wednesday, Wednesday, Thursday, Thursday, Friday, and Friday, Saturday. So there are total 7 pairs for the 2 neighboring days, extra 2 neighboring days. But our interest is we should have, the year should have 52 Sundays. So in those 7 possibilities, the cases favoring the Sunday are Saturday, Sunday, and Sunday, Monday. So there are 2 favorable cases. So the probability is number of favorable cases by total number of cases, that is 2 by 7. So probability of having 53 Sundays is 2 by 7. And probability of having only 52 Sundays means the complementary probability, that is 1 minus probability of 53 Sundays, that is 1 minus 2 by 7, that is 5 by 7 only. So in this way we can find the probabilities by using the classical definition of probability. In the same way, by using additive law, we can find the probability of getting a 2 or a 5 when a die is rolled. Die has 6 numbers. Okay, so the probability of getting 2 is 1 by 6 and the probability of getting 5 is also 1 by 6. And 2 and 5 are mutual exclusive. That is, if the die shows 2, it will not show 5. If the die shows 5, it will not show 2. So those 2 are mutual exclusive, and hence by axiom of union, P of 2 union 5 or P of 2 or 5 is nothing but P of 2 plus P of 5, and hence 1 by 6 plus 1 by 6, and hence the answer results into 1 by 3. So with this, I'd like to conclude the first lecture on probability. In this lecture, we studied the fundamental concept of probability, and we have seen some examples of finding probabilities by using classical definition and additive law. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.